On for the introduction. Welcome to my presentation on grid integration of renewables into weak grids. Um, well, let's start with a brief outline of this presentation and what we are going to look at. I will start with a section on weak grid integration of converter interface generators into weak grids and see what challenges there are and what are the issues that we might actually face when we are going to integrate such resources into weak grids. We will then move on to some stability analysis of and grid strength and an index actually that we have developed to see when a converter connected asset might be unstable in a weak grid, and finally a self-synchronization loop of PLLs in such networks. Then I'll move on to frequency control in low inertia systems using some grid following inverters that would be similar to your FGAS services that you might have in a system, and a framework that we have developed using synchrophaser or PMU data to control the frequency of the network. And I'll talk about the framework and some performance analysis. And finally, some grid strengthening solutions, in particular SynCons and grid forming inverters. I'll be talking about them and how they can help us to stably operate in a weak grid. So let's start with the grid strength issues and see what problems we might face when we are going to integrate power electronic connected assets to the network. Well, first of all, what is system strength? System strength tells you how your power system will react when there are contingencies in the system, how reliably and securely your power system can operate when you've got, let's say, a fault in the system, a generator trips, you've got a load connected or a load shed in the system, how your system will operate. To the right, you can see the NEM, and the dots actually indicate the situation in 2019, pretty recent, as indicated by actually a MIMO. So if you look at these parts here, these are pretty weak parts of the network in northern Queensland. Also, we've got quite a lot of red dots in South Australia, and in particular in northwestern Victoria, West Mara region. And Tasmania also is not it's not in a very good shape in terms of system strength. In 2029, as predicted by AEMO's ISP integrated system plan, the situation will be even worse. We'll have more of these red dots, and in 2039, the situation can be catastrophic, as again predicted by AEMO's ISP. Tasmania, quite a lot of red dots in Victoria and almost everywhere. We've got some, actually only a few green dots, which indicates high system strength. Well, the bad news is that most of our renewable energy zones are actually either in places where we do not have any transmission lines, or they would actually be in places where we've got lots of these red dots. So these, it would be very challenging if we want to add renewable energy resources to the grid, because most of them would fall within these very low system strength regions in our network. But what are the problems? Well, as actually identified by one of the CGRE reports, it was a report on integration of renewable energy farms into weak networks. These are the issues that we might face. Well, control interactions and instability, failure to write through, electromechanical oscillatory stability, islanding issues, SSOs, self-synchronous oscillatory behavior, inability of farms to inject their maximum power, and well, and many more actually that I haven't listed everything here, but these are quite important. A couple of months ago, AEMO actually had to slash a few of the solar farms, probably you've heard of, because they were operating in a very weak region and they were oscillating, actually they were creating some oscillatory behavior in the system. So their maximum power had to be slashed to half, which is actually a big loss for these farms. Well, we know all of these problems, but we yet don't know exactly when these issues will happen, under what scenarios these issues will happen, and yet we are struggling to very accurately predict when and under which value ranges we will have these issues. And what we have in the industry at the moment is pretty conservative. And You know, we've got a few solutions, as I will be talking about them in this presentation, mainly towards the end, but yet there is a long way to be gone for the, in particular for research and development, before these solutions can be very well adopted in industry. Now let's have a closer look. What services do we require for a power system to operate reliably and in a stable manner? Well, um, mainly four different services: inertia, system strength, voltage control, and frequency control. These are what you would need for your power system to operate stably. And traditionally, synchronous generators, they would give us all of these things. And well, like 20, 30 years ago, when we didn't have much of these converter connected generations, we didn't have any issues really. I mean, it was all planning and how to deal with uncertainties, but not much of a stability issues from the grid strength point of view. But now that we are replacing all of these synchronous generators with some converter connected or power electronic connected generators, we are having all sorts of issues. And in order to provide these services, we are hoping to actually use some more modern technologies in order to provide us all of these four categories. In particular, what is very interesting, if you look at all of these things, synchronous condensers and grid forming inverters, they repeat in all of these. That's very interesting to see. And of course, for each of these pillars, you have some other solutions, but again, SynCons and grid forming inverters, interestingly, can provide you with all of these, and I will be focusing on them down a little bit after in my last section. Now that we know a little bit more about grid stability, let's do a little bit more analysis on a grid-connected asset and see what is the cause of the problem. So this is a VSC, voltage source converter, connected to the grid, and I've got a vector current control. This is a grid-following inverter, which means that I would need to have a PLL to be synchronized with the grid, and a vector current control will control the real and reactive power of my grid. Well, if I look at the PLL, this is typically a PLL which is used in many different applications. Of course, there are so many different types of PLLs, but this is a very common PLL, which is called SRF PLL, or synchronous rotating frame phase lock loop. And what it does essentially, it forces your VQ to 0, which means that your ID will be proportional to your real power and IQ proportional to reactive power. So it's a nice and decoupled control of real and reactive power. However, if you look closer, in the literature, you can actually find this self-synchronization loop. So there's this self-synchronization loop. You can model this, and this self-synchronization loop actually tells you that if your grid is weak, so if you've got a grid which actually has some impedance, and I will call it the grid loading effect, it will appear in this phi omega. And here, this is the converted current. So the higher the converted current is, and the higher the impedance of your grid is, the impact of this self-synchronization loop will be more actually pronounced, and you have some sort of positive feedback loop, which can lead to instability in your system. So this is the reason why you will have difficulties connecting to the grid when you've got a grid following inverter. So if you look at this, if you write all of the equations for this grid following system, you can actually come up with a state space equation for this. Actually, what we've done in this work, we have taken the self-synchronization loop that I've just shown before, and we've written all of the equations, and we've come up with this state space equation, which can actually tell you all of the dynamics of the system. And the beauty of that is it can very, in a very nice way, capture all of the dynamics of this system and all of the parameters that you've got in this system. Well, including the phase angle of the current. Well, that can be, well, this is your power factor. This is the amount of the power, the current that you've got, the filter of the network. Well, this should have been LG. And these are the parameters of your PLL. And also, you can also have your resistance of the grid included here. So all of the parameters that you've got in your system can be captured in this dynamic. And what we did What we did actually, we used Lyapunov's first stability theorem in order to find a guaranteed stability boundary for this system. And what we actually ended up having is something like that. So if you rearrange this, you can come up with this DFSM, which is actually a boundary here, distance from stability margin. That's what we called it. So this DFSM can be written as this relationship here, and if it is positive, it means that your system is stable. So what we did, we actually tested this for a system, and actually for this particular values here, and the predicted boundary is this yellow, sorry, this blue line. So this is what we predicted with our DFSM. So I go back here one more time. So this is the DFSM that we determined. So it is a function of all of the parameters and variables that you've got in your system. And also we verified that with some simulations, and we found these real boundaries. And you see there is a pretty good match that if you want to pass this, if you want to go beyond this, your system will become unstable. Also, what we did, we increased R being the resistance of your grid, linearly from 7 ohm, and the system was stable at 7, and up to 13.2. At that point in time, which I think it translates to this point, the system became unstable, exactly as predicted by this point here is 12.5, and 13.2 is the point here. So at 12.5, we predicted that the system should be unstable, and it became unstable. We did also another test for increasing L, and we increased our L from 10 millihenry to 25 millihenry. Again, the same thing happened when we predicted that the system will be unstable at L equal 25, and it became unstable at that point in time. We actually then said, okay, what can we do to actually remove this loading effect of the grid? Of course, again, I should emphasize there's so many different ways of getting synchronized with the grid. And what I'm doing here and the analysis that we did is valid for an SRF PLL, synchronous reference frame PLL, where you are actually forcing your VQ to 0. But if you are using another PLL, well, the result can be different. But what I'm again showing is for that particular PLL. So we said, okay, we know that we've got this loading effect. We have this self-synchronization loop for our PLL, and we know that it is a function of current. It's a function of the grid impedance. We know what the current is. We can somehow estimate the impedance of the grid, so why not compensating for that? So what we did, we added this loop to a normal PLL, a conventional PLL, to compensate for the impact of the self-synchronization loop in the system. So essentially, we estimate the impedance of the grid, and we know what is the current of the converter, and this Kc is in a magnitude of the actually grid impedance. So we can compensate for that. But, well, there is one problem in this, that you need to somehow be able to estimate your grid impedance. Either you should know where you're getting connected to, and you can probably know the SCR and XR ratio of the grid at that point, which is a common index, and probably it is known to you. So you can use that. Or if you have no idea about the grid, you potentially could do some sort of identification in order to find out what is the grid impedance, so that you can put it into this compensator and compensate for the self-synchronization loop in order to increase the stability margin of your system. So we did that, and in simulation, so this was our conventional PLL, we actually had a jump in our current, and the system was not able to maintain its stability. The PLL would go unstable, and of course your ID and IQ would be unstable, meaning that there will be a lot of oscillation in your real and reactive power. With the compensated PLL though, we could very well compensate for the self-synchronization loop of the grid-connected VSC. And as you see upon a change in the current, in, for example, D component, everything is fine. We can track the reference very well. And there are, of course, some oscillations in our frequency. After all, it's a very weak grid. but we can maintain the stability of the system. We also did some experimentation here, so the same thing. We actually had a conventional PLL and we increased the set point for ID, but the system became unstable and the PLL could not track the frequency anymore. But in the compensated PLL, after some transients which will decay, the system became stable and actually could maintain stability. Well, needless to say, that estimation of grid impedance plays an important role here. So if you know your grid impedance, it means that you probably can use this compensator in order to compensate for the loading effect. Now, again, I want to emphasize that this is for a particular type of grid synchronization, and it may not be applicable to other grid synchronization techniques. And I know that different manufacturers, they've got different types of synchronization techniques. We are currently working on an alternative synchronization technique, which I'm not going to present here. It is still in research phase, but very briefly, it is somehow a competitor of an FFT, let's say, approach that can very accurately predict your 50 hertz signal, but it is not FFT. I'm just saying that in terms for comparison, it's not similar to a normal PLL that I presented here. It's kind of like, from performance point of view, similar to an FFT, and the initial result has been very, very promising. The super weak grid, we managed to get synchronized with the grid and maintain the stability. Of course, there's some prices to pay. The method is much more complicated and computationally heavy, but so far the performance has been very good. Yet again, I just wanted to say that your synchronization plays a very important role when it comes to grid following inverters. So that's the key, and that's the main source of instability in such systems. Now, we know what happens in these weak grids, and we know why these systems become unstable. And most of these systems are already in place and operating in the grid, and we can't do much about them. They are there, they are producing power. Now, you need to make sure that the grid is strong enough and can stably operate. So there are a few solutions, and one solution would be providing different types of frequency control in such low inertia systems. So in this section, I'm going to go through one frequency control approach that we proposed for battery energy storage systems. And this is, again, some sort of grid forming inverters, meaning that I've got a grid forming inverter connected to a battery, and it is going to control the frequency of your system. And later on in the next section, I will talk about approaches that can actually help us to strengthen the grid without using grid following inverters. But first, how are we going to do this? We are going to use PMUs in this approach. So you know probably what PMU is. PMU, if I want to describe it in a very primitive way, it's a sensor. It's a sensor for sensing your frequency. So imagine that you've got a power system. There is a step change or any change in your real power, and this real power change will actually be translated into a change in your frequency. Now, if you've got PMUs in different parts of your network, they can give you a very nice and synchronized measurement of the frequency at that point, and they will be all synchronized with a common time. Now, the idea in this approach is to use PMUs and actually get the readings and get what they are giving you first in order to identify a model of your system, and also use that model in order to design a controller which would eventually give you the set point for the power of a battery energy storage system in order to control the frequency of the grid. So what we did, we actually excited our power system at a given point, and that system excitation is nothing but a PRBS signal, and that PRBS signal was actually on top of the set point for the power, and it would give us some oscillations in the frequency. We would actually get the data and identify the model. Then, using the identified model, we actually use a robust control design method in order to design a controller that would give us satisfactory performance for our controller. Sorry, just lost the headphone. And this will give us a controller which would result in a satisfactory performance in terms of changes of power, which would then regulate our frequency. And then we would use that controller in order to close our loop. So I've got a frequency set point, for example, at the point of common coupling of my battery energy storage system. I would get the frequency from my PMU. Then I'll create the error, give to the controller that we design using this approach, and it would actually then be applied to the power system in order to control the frequency. So this is actually a schematic diagram of that, how it works, and what we wanted to do. We wanted to have 4 different batteries in different areas in the NEM. So this is Queensland, New South Wales, Victoria, South Australia. So we've got 1 battery in each region. And we would actually assume that we've got PMUs in the system, that they would give us the information of the system into a controller, and then each of these batteries can then inject the amount of power that they would require. Now, how did we do the identification? Well, we implemented or simulated the system in Opal RT. We simulated this multi-machine power system, which is very similar to the southeastern power system of Australia. But what we've done here, we have augmented this with different solar and wind farms so that it would be a low inertia system, and all of them are converted type generation with power electronic converters. And they are mapped with 16 zones as actually given by AEMO's National Transmission Network Development Plan. Now we've got 4 different battery energy storage systems, one here, one here, one here, and one here, and a PMU is connected to each of them at their point of common coupling. Now, you can then find a model for your system. So of course, it's a multi-input, multi-output system, and we excite one of these systems at one point in time. So every time one of these batteries is exciting the system, and then we can get the model of the system. So we assume that we've got 4 batteries and 4 sensors as PMU. So we've got a 4x4 system. So 4 frequencies and 4 power set points for each of these batteries. So we get this 4x4 model of the system, and then we can design a controller based on these non-parametric models that we have obtained. So it's I don't want to go through the details of this, otherwise we won't have time, but very briefly, so first we excite the system and we actually do the identification. And then based on the model that we have identified, we find an initial controller, and then based on the initial controller, we want to come up with another controller that would give us the performance that we want. And actually these performances are like, well, we've got robustness, disturbance rejection, and stability. They're all formulated into a control design using different actually constraints in an optimization problem, which would minimize the sensitivity function of the system. So that would give us good disturbance rejection and a good stability margin for our system. And this is some sort of iterative control design. So we start with an initial controller, which is a droop controller in this case, and then we increase the order of the controller with some constraints. And one important constraint for us is that the DC gain must still be similar to droop system, so that the DC actually behavior or the steady state behavior of these are still the same, and they're sharing power among them, similar to droop controller. And well, we designed this controller using this optimization, and let's see how it actually operates in real life. So what we did in order to make it even more realistic, we used some real PMUs. So we used actually a hardware in the loop experiment. So we've got our Opal RT here. This is our real-time simulator in which we have simulated the system. We've got some real PMUs and from PSL. And this is, of course, synchronized with a UTC with its GPS antenna, and it is actually one of the PMUs in the system. So we've got 3 more PMUs in the system, and they are software PMUs, but we've got also a real PMU, so to give us this hardware in the loop experiment. And we actually have also the concentrator for the data that we get. Of course, it's an open PDC in a host PC, and we've got the communication over a common Ethernet network. So we did the model identification in a dedicated PC, of course. We got the data from the real-time simulator. We stored them in a PC. We did the model identification, and then we did the control design, and then put the controller back in our simulator to see how it operates. Well, we did a few tests. One of them is here. So we wanted to see how our controller will respond to some load changes. So we had a load change of 360 megawatt in the system. So the blue one is if you don't have any controller in the system. The red one is when you have a 3% droop, and the other one is the H Infinity controller that we have designed, and this H Infinity controller is giving you a better nadir in frequency and a better actually steady state frequency. And you might wonder, okay, what if you increase your actually droop coefficient? You might get a better response. Well, yes, but in this case, 3% was the maximum that we could get before the system becomes oscillatory and behave in a very well, would actually impose some SSOs in your system. So in order to get similar responses without any excessive oscillation, 3% was the maximum we could get, but the H Infinity could get us a better result. And these are the different batteries that we've used in different parts of the NEM. So in the battery in South Australia, Victoria, New South Wales, and Queensland. And of course, the closer you are, I mean, the closer your battery is to your contingency, which is a load change here, the more its output will be, of course, to respond to this. Now, another test was a generator trip. More or less similar scenario. We have lost some generation, and in this case, again, the H Infinity can actually operate better and result in a lower nadir. And here you can see the output of different batteries that we've got. Okay, so after looking at this frequency control using batteries, which is again, after all, another type of grid forming asset in the network. It is a grid forming asset in the network which is trying to help you to control the frequency of the system in order to help other, of course, assets in the network to operate stably. But yet, these grid following inverters connected to these batteries are not really a part of giving you system strength, or they're not forming your grid. They are actually trying to help you to actually control your frequency, but they're not able to give you everything. So better than batteries that are in a grid following mode and are only, for example, reacting to changes in your power, it's better to use other technologies that can give you different services at a time. And two very important solutions these days are synchronous condensers and grid forming inverters. You probably have heard of them, and I'm going to very briefly introduce, well, synchronous condensers and to see what they are and how you can place them in the system. But more importantly, we will be looking into grid forming inverters today. But what is a synchronous condenser? A synchronous condenser is essentially a synchronous machine without a prime mover. So what it does for you, it doesn't really give you real power. So it's not really like a synchronous generator. So it doesn't have any prime mover in order to generate real power, but it can actually give you reactive power. It can give you voltage support because it does still have its exciter, and it can also provide inertia. And you would ask, okay, you don't have a prime mover, but how can you provide inertia? Well, you can add a flywheel to that, and that's how people do it. They add a flywheel to this synchronous machine without any prime mover so that you would have some inertia depending on how much inertia you would need. Well, what are the drawbacks? Well, installation and operation costs. It's a pretty expensive solution, and lead time. It's not easy to get one. So if you need it today, if you're lucky, you might get one in a year from now. So it's not easy to get one of them installed in your project if you're desperately looking for system strength in a particular point in your network. That means that if you want to invest in one, you have to actually optimally allocate them and optimally size them so it would give you what you want. So what we did in a project, we actually looked at an optimal allocation and sizing of these SynCons. So we've done actually two pieces of work. I'll be presenting one of them here. The other one is being actually prepared for publication at this point in time. But very briefly, I'll talk about this one. So we actually defined a cost function and objective function actually for us to be minimized. And there are two main parts for this function, F1 and F2. So your F1 is the cost, different costs associated with your SynCon. Of course, you've got your installation costs, you've got the operating costs, you've got different types of costs here, and also some sort of cost that would be incurred because it will change the power loss in your system as well. Also, we have the second function here, which is a function of the voltages at different buses, because you would like to also maintain the voltages at a given value. And the constraints that you've got, well, of course, you want to know what is your like what is the capacity of your SynCon, and additionally, you would like to have another constraint here. Sorry, the constraint are, this is my constraint. The constraints are for SCR to be minimized. Well, what is the idea of putting a SynCon? You would like to minimize your SCR in the system. You would like to actually, sorry, you want to maximize the SCR in your system. So the minimum SCR in the system should be more than a given value. So in a nutshell, you want to put these synchronous condensers in different parts of your network, and you would hope that you minimize the cost and maximize the SCR in different nodes in your network. So that's how we have actually formulated this approach and this optimization problem, and we have applied a few heuristic optimization algorithms to this one. But the other approach that we are taking at the moment, we are reformulating this problem entirely, and it will be taking into account different aspects of the system and the impedance of the grid, in a sense that it would be more accurate in terms of SCR minimization, and it will have SCR in the cost function rather than constraint. So we are hoping that the second approach would give us a better optimization or optimal allocation. But I will be only talking about the optimal allocation of this method that the first one that we did. And we actually created this model in PSCAD. So it's an augmented IEEE 39 bus, and we have added wind turbines and solar farms at different buses in this system. And we wanted to see where we should install a SynCon to give us the best performance. So this is the test results of that system without having any SynCon. So you can see that up on some faults, for example, a fault at bus 29, up on the recovery, we've got some oscillations in the system. And also we've got some about 12 hertz oscillation at bus 29, and also at bus 32 we've got 3 hertz oscillation, 38 also we've got 3 hertz oscillation, and of course the system is unstable up on the clearance of the fault. But after finding an optimal location for our SynCon and installing that in the system, we are having a better actually a response, and the system can very easily recover from the fault. We are also working on the exciter of the SynCon at the moment, but still this is work in progress. So the exciter of the SynCons are very important in how they respond to different faults in the system. Typically, some sort of droop control is used in exciter of SynCons in order to respond to different contingencies in the network. And taking an approach similar to what I explained for our batteries, where they were controlling the frequency, we're taking the same approach, and And when I say the same approach, I mean in terms of control design. We are identifying our system by exciting, and we are hoping to design a controller based on a droop control to give us better performance. And in particular, we are hoping to damp subsynchronous oscillations when the system is recovering from a fault. And this is the block diagram of what we are working on at the moment. We are hoping to actually redesign this controller here in order to give us a better performance. So this brings me to the last part of this presentation, which is for myself the most interesting part, grid forming inverters. So far what we've talked about, we talked about well, weak grids and what problems we've got in weak grids. And we saw that how a grid-connected VSC will have difficulties in maintaining its stability, mainly because of the synchronization unit, the PLL it has. And we saw that when it will become unstable, we had a solution for that. We moved on to frequency control using batteries, and also we talked about SynCons to strengthen the grid. But in my opinion, the most interesting solution for all of these problems is actually grid forming inverters, which is a technology which is a direct competitor of SynCons, but based on power electronic technology rather than relying on the very old technology of synchronous generators. But how does it work? Well, imagine that I've got this system. Imagine that I've got a power electronic converter connected to a load and a line filter. Well, I know that I can have a current control in here, and this is more or less similar to what I described in the beginning of the presentation. So this current control, you probably are familiar with that. It can control the ID and IQ components of the current for you. Now, if you have a secondary loop, so some sort of a cascade loop, you can control the D and Q components of this voltage here. And if you give any reference value to this, and in particular, if you give a frequency set point here, you can control that voltage at any frequency and any amplitude that you want. Now here, this is an islanded system. I'm connecting this VSC to a load, but if instead of this load, I had a grid. So if I was connecting this to a grid, and of course the grid has some impedance, so this voltage here is now fully controllable, right? I'm using this system, this control system here, using a cascade loop for current and voltage. I can fully control that VABC there. And we know that in a power system, when we've got two systems, two AC systems connected to each other, we can control the power, and that power is V1, V2, sine delta, delta being the phase angle between these two voltages over X, X being the impedance here. So in this case, if I change that voltage VABC, and if I play with that, and of course the voltage here is fixed, this is a grid, an ideal system, let's say an ideal voltage source, I can manipulate the voltage, the power transfer between my VSC and the grid without relying on any PLL. So essentially, I'm actually having a system here that doesn't require PLL, but still can actually exchange real and reactive power with the grid, and that's the basis of grid forming inverters. However, on top of what I've just described, which was a current control and a voltage control, in a grid forming inverter that you want to connect to the grid, you've got a primary control level as well. And that primary control level, essentially what it does, it actually, with a power controller, power calculator, it calculates the real and reactive power at the point of common coupling, and it gives to a primary controller, and that primary controller would tell you how much voltage you would put on this capacitor here in order to achieve a particular power exchange with the grid. Now, if we look closer, there are two main types of primary controller in the literature. One of them is droop control, one is VSG control. Droop control is probably known to you. VSG control is, well, in terms of reactive power, they're identical, VSG and droop control, but the real power loop is slightly different. However, if you look at them more carefully. In particular, this part, which is the swing equation of the voltage source, sorry, the VSG control is still equivalent to this if you write the equations, and if you choose this omega C here and this KP here, and if they will be equivalent to this system here. So essentially they're kind of equivalent. The difference is mainly in this governor here. So if we don't have any governor, these VSGs and droop controls are the same. But these are the two main ways of primary control for grid forming inverters in the literature. Now, what we're doing at the moment at Monash, we are designing a new family of these primary controller. So what we've done, we've modeled the system, and this is the model that we have derived for a grid forming inverter. And if you look at the frequency response, this is how it looks like. And using the approach that I described previously, we have identified, well, you can either identify or have a parametric model, doesn't matter. And then we have taken the same approach of designing a controller based on a given performance in an optimization problem in a reiterative way. We have taken droop control as the initial controller, and we have come up with a control design that can help us to design a primary controller for grid forming inverter, which can give us a better performance. So this is my grid forming inverter. So this is connected to a grid. This is my grid forming, and this is the capacitor here. And the idea is to see how it works in islanded mode and grid connected mode. One thing that I forgot to say is that your grid forming inverter is supposed to work in both islanded mode and grid connected mode. And typically, a VSG has better performance when it comes to an islanded system in terms of ROCOF, rate of change of frequency, and a droop control has better control when it comes to grid connected mode. So if I look at here, this is a case in which we've got a grid connected system. So it means that this switch is closed, and we've got a 10 kilowatt set point change for this system. So the blue one is your droop control. VSG is the red one, and the controller that we designed is the yellow one.
All right,
So
15 minutes to go.
yes, fantastic. I think I hopefully will be finished in 5 minutes, so we will be very well on time and we can have time for discussion. Thank you so much for the reminder. So if you look at the blue one is your droop controller, and upon the change in your set point, it can very well track the set point. So that is actually the good point about your droop control. It doesn't have any excessive oscillation, and it has a very nice behavior in grid connected mode. However, if you look at your VSG, it has a lot of oscillations before it actually settles down into the set point. The controller we designed is something in between, so it is actually pretty fast, pretty good, but it doesn't have excessive transients. Now, you might say, okay, droop is better, but you need to also look at the islanded case. In the islanded case, droop does not really give you any sort of inertia. It doesn't give you much of ROCOF control. So if you look at the ROCOF, rate of change of frequency upon a step change in your load in the islanded mode, when this is actually open, when this switch is open, your droop doesn't give you good performance. Actually, it gives you terrible performance, and it has a very, very bad ROCOF, which easily can trigger some protection systems to actually do some load shedding in order to maintain this stability. But if you look at VSG, it has a better performance, of course, compared to droop, and our controller is even better than VSG. Initially, the ROCOF of VSG and our system are kind of the same, but our system even slower reacts to this change in the load, and it gives you a better ROCOF. So it is, if you look at these two cases of grid connected mode and islanded mode collectively, you can see that the H infinity design method is giving you a better performance, and actually it is a better controller collectively for both of these cases. And why is it important to have good performance for both of these cases? Because simply you don't know when and under which scenarios you might be in islanded or in a grid connected. You might mainly operate in grid connected, but there is a contingency or something, and you might go to an islanded mode. So your controller must be able to give good performance for both of these cases. Here I have some comparison between these two cases. So if you look at the droop control in terms of overshoot, of course, in grid connected mode, this is the best, no overshoot. But our method in terms of overshoot is better than VSG. And in terms of settling time, we're also better than VSG. But when it goes to islanded mode, droop has such a high ROCOF. But our method and VSG, they both have pretty good performance, and we kind of have the best of the both worlds. So it is a system which can be used in both islanded and grid connected and give you very good performance in both of them. Lastly, before I finish, I wanted to show you how these SynCons and grid forming inverters operate in the system. So this is a very simplistic block diagram of a system that we were working on. We had an industry partner here, and this is actually a realistic system, but I'm not going to disclose the information about that. But just we had a solar farm, and that a solar farm was supposed to be supported by your SynCon or a grid forming inverter to be connected to the grid and react well upon contingencies in the system. So here you can see the results without anything, without any SynCon or a grid forming inverter, and the grid was all right. It was not very weak, but it was not strong neither. So, for example, for this case here, for the two cases, so the first one, actually these are the voltages and these are the powers, and this is one test, this is another test, and this is another test. So that's how these figures are actually put here. So in the first test, we've got a three-phase fault to ground. So the voltage drops actually from around 1 per unit to 35 per unit. And this is how the system recovers. And you've got a lot of oscillations here. And when there is a set point fall, you can see that there is a lot of oscillation here. And when there is a fault, you see that the system doesn't operate very well, and you've got quite a lot of oscillatory behavior. And this is what happens without putting any SynCon and any grid forming inverter. And yet again, I have to emphasize, this is not a very weak grid. This is a grid which is weak, but not very weak. Now, what we did, we wanted to compare addition of a SynCon or a grid forming inverter. So if you look at the red one is a grid forming inverter added to the same system. The blue one is a SynCon added to the same system. So if you look at, for example, this one here with the three-phase fault to ground, so yes, SynCon can operate, can actually recover from the fault with lower voltage spike in the system. If you look at this, the grid forming inverter has some bad spikes here upon the recovery. However, SynCon is giving you those oscillations, self-synchronous oscillations upon recovery in this case. Having said that, although the spike of the grid forming inverter is not so good, it is very easy to actually get rid of this spike. The reason we didn't get rid of them because we were using a commercial product, we were using a commercial simulation platform, and we could not change anything inside. But one of our research streams at the moment is virtual resistance for different types of grid forming inverters, and using those, you can very easily damp the spike that you get up on the fault recovery. We actually have a generic model, and we tested on the generic model, and we could very well damp the spike that you get here up on the recovery. Another test is, well, set point fall, and as you can see, the grid forming inverter can operate much better. So it is much smoother upon that set point change, but SynCon would impose a lot of oscillations in the system, which is not great. Grid voltage falls, so the grid voltage here falls from 1 to 95. You can look at it again as some sort of fault in the system. So again, the grid forming inverter has a higher spike here. Again, a virtual resistor can help you to actually have a better response, but your SynCon is not as good. But needless to say, all of these are better than not having any SynCon or grid forming inverter, and give you much better performance compared to the case where you've got only your solar farm connected to the grid. Okay, so that concludes the presentation, and I believe we are very well on time.
Cool, thanks, Behrooz. Are there any
Yes.
questions for Behrooz?
Hi, Behrooz.
Hi.
Okay. Yeah, thanks a lot for the presentation. Really enjoyed it. I'm not expert in power systems, so I have a very basic question. So roughly speaking, so what is the sampling time for frequency control in your simulation, and also for the last part simulation? So roughly speaking, what is the sampling time for the control loop?
Well, the control, well, because we've got a few different controllers here, maybe if I go back actually, let me go back to where I was talking. Yeah, this is probably very good. So you see I've got this inverter current control. So this inverter current control is the fastest loop that we've got in a grid forming inverter. This loop, it typically has a rise time of around, it can easily be around 1 millisecond. So the rise time is 1 millisecond. Typically, the sampling time that you would use for this controller, the inverter current control, the sample time is around 100 microsecond to 200 microseconds, so 10 kilohertz, give or take. The capacitor voltage control, it's a, well, this becomes like a cascade loop here. Typically, that one would also operate with the same sampling rate. So the sampling rate for that would be also around 10 kilohertz. But of course, the rise time for this controller is slower. Typically, we put like 10 times slower than your inverter current control. Now, the primary control that you would put here, they are even slower. So typically, their sample time is in the order of millisecond, or you would put them 500 microsecond to millisecond. And they are also, of course, slower in terms of response time. And if I want to show you the response of that is here. So you can see that this is these are in second. So it takes, for example, half a second for that to respond to changes. So that's what you would get in terms of response time, but in terms of sample time of the control of those is around millisecond or so.
Okay, I see.
Yes.
I see, thanks. I'm asking because I'm wondering if you have thought about like using constraint control techniques.
What is that?
So for example, you need to solve optimization problems online.
Oh, yes. No, we actually didn't do that. No, all of these examples that I have explained so far, you would do some sort of, if you want to design a controller, you would do the optimization, everything offline. You do a test, you obtain the model of the system, and then you do an offline optimization for control design. You get the coefficients of the controller, and you just put, the controller can be maybe a transfer function, depending on the performance you're after, but the transfer function could be first order or second order, third order transfer function that you would put there, and that's it. There is no adjustment. So there is no, it's not really adaptive control. It's not any sort of control that would change the gains or change anything on the go. But of course, that's a possibility, and most likely it will increase the performance, but of course, it will make things more complicated, and of course, you would need to pay for a more probably sophisticated platform to be able to implement that as well.
Yeah, sure. I see, yeah. Thank you. Yes,
yes,
maybe I'll contact you later. And
sure, absolutely.
further questions.
Sure.
Thanks, Behrooz.
Yes.
Thanks. Yeah, you asked half of the question I wanted to ask, so it's fine. Is there any other one with a question? Okay, if there isn't any more questions, let's thank Behrooz again for his talk, and
Yes.
see you everyone next week for our
Yes.
talk. Thanks.
Thank you so much. Have a good one.